Timeless Concepts from Physics Helpline. This is a video tutorial series through which we will sharpen our problem solving skill. First, we will analyze the problem on hand to find the related concepts. Then using these, we will develop a method which will produce the solution. This will help the students aspiring to get into IIT to understand the much needed advanced theories and applications in physics. In this video tutorial, we will discuss the second part of the theory of alternating current, in which we will understand the behavior of a single circuit element like a resistance, a capacitance, or an inductance when connected in an AC circuit. First, let us understand the behavior of a resistance connected to an AC source. The instantaneous voltage of the source is given by E is equal to E0 sin omega t, where E0 is the peak voltage. This is also the voltage across the resistance R. Let I be the instantaneous current through the resistance. Then, by Ohm's law, we have I is equal to E by R, which is equal to E0 by R sin omega t, whose maximum value is E0 by R. Therefore, we put it as equal to I0, which gives I is equal to I0 sin omega t. From the equations for voltage and current, we understand that when omega t is equal to 0, both voltage and current are 0, and when omega t is equal to pi by 2, both attain their maximum values. Hence, we conclude that voltage and current are in phase in case of an AC circuit containing a resistance only. The sinusoidal variations of voltage and current are shown in the first figure. The second figure is a phasor diagram in which current and voltage amplitudes are represented as rotating vectors. In case of pure resistance, both the vectors are pointing in the same directions. Now, an inductance L is connected to the AC source, whose instantaneous voltage is given by E is equal to E0 sin omega t. At that instant, let the current is equal to I, and rate of change of current in the inductor is equal to di by dt. Therefore, magnitude of voltage across the inductor is L di by dt. Since there is no other circuit element, voltage across the inductor is equal to voltage of the source. Therefore, we write L di by dt is equal to E0 sin omega t, which implies di is equal to E0 by L sin omega t into dt. Therefore, integral di is equal to E0 by L integral sin omega t into dt. Now, integral of sin omega t is equal to minus cos omega t divided by omega. Therefore, we have I is equal to E0 by L into minus cos omega t divided by omega plus the constant of integration. Therefore, we write I is equal to E0 by omega L into minus cos omega t plus constant. Now, cos omega t may be written as sin pi by 2 minus omega t. This implies minus cos omega t is equal to minus sin pi by 2 minus omega t. Here, we use the identity sin minus theta is equal to minus sin theta, which gives minus cos omega t is equal to sin omega t minus pi by 2. Also, the maximum value of I is equal to E0 divided by omega L. Therefore, we put it as equal to I0. And since voltage changes symmetrically about 0, current will also have the same variation, which means that the constant of integration must be 0. Here, we note that omega L is the inductive reactance represented by XL, which has the dimensions of resistance. Therefore, we write I is equal to I0 sin omega t minus pi by 2. The sinusoidal variations of voltage and current are shown in the first figure. We observe that when omega t is equal to 0, E is equal to 0 and I is equal to I0 sine minus pi by 2, which is equal to minus I0. When omega t becomes pi by 2, E is equal to E0 sine pi by 2, which is equal to E0 and I is equal to 0. Therefore, we conclude that current lags behind voltage by a phase difference of pi by 2 radians. This is indicated in the second figure. Now we connect a capacitance C to the AC source whose instantaneous voltage is given by E is equal to E0 sin omega t. At that instant, let the charge on the capacitor is equal to Q. Therefore, voltage across the capacitor is equal to Q by C. Since there is no other circuit element, this must be equal to the supply voltage. Therefore, we write Q by C is equal to E0 sin omega t, or Q is equal to CE0 sin omega t. Now, current in the circuit is equal to rate of change of charge on the capacitor. Therefore, I is equal to dq by dt, which is equal to CE0 d by dt of sin omega t, which is equal to omega CE0 cos omega t. Rearranging, we get I is equal to E0 divided by 1 by omega c into cos omega t. We observe that the maximum value of current is equal to E0 divided by 1 by omega c. Therefore, we put it as equal to I0. Here we note that 1 by omega c is capacitive reactance represented by Xc, which has the dimensions of resistance, and we use the identity cos omega t is equal to sin omega t plus pi by 2. Therefore, we get I is equal to I0 sin omega t plus pi by 2. The sinusoidal variations of voltage and current is shown in the first figure. We note that when omega t is equal to 0, E is equal to 0 and I is equal to I0 sin pi by 2, which is equal to I0. When omega t increases to pi by 2, E becomes E0 and I is equal to I0 sin pi, which is equal to 0. Therefore, we conclude that current leads voltage by a phase difference of pi by 2 radians. This is indicated in the second figure. This completes the theory of alternating current circuits containing only one circuit element.